Chapter 14, Temperature and Heat Transfer. This lecture will help you understand specific heat capacity and the method of mixtures. Specific heat capacity is defined as the quantity of heat required to change the temperature of 1 unit mass of a substance by 1 degree. It is a measure of the thermal inertia that indicates the resistance of a substance has to change in temperature, sometimes simply called specific heat. Substances have their own specific heat capacities. For example, the filling in a hot apple pie has a greater specific heat capacity than the crust. Watery filling has more capacity for storing heat than the pie crust. Water has a higher capacity for storing energy than almost any other substance. How much heat is stored involves various ways that energy can be absorbed, such as an increase in the jiggling motion of molecules, which raises the temperature. For water, an increase of the amount of internal vibration or rotation within the molecules can become potential energy, which does not raise the temperature. Since water can absorb so much energy as potential, water molecules can absorb energy without increasing the translational kinetic energy. Increasing the kinetic energy raises the temperature, but increasing the potential energy does not. The amount of energy that raises the temperature of 1 kilogram of a substance by 1 Kelvin or 1 degree Celsius is called the specific heat of that substance. Each material has a different specific heat. A specific heat formula is Q equal mc times delta T, where Q is the amount of heat added in calories or joules, m is the mass in kilograms or grams, C is the specific heat or specific heat capacity in calories per gram degree Celsius, or kilocalories per kilogram degree Celsius, or joules per kilogram degree Celsius. Delta T is the change in temperature in degrees Celsius. In the U.S. system of measure, specific heat is the amount of energy that raises the temperature of 1 pound of a substance by 1 degree Fahrenheit. Specific heat formula is Q equal WC delta T, where Q is the amount of heat added in BTU, W is the weight of the substance in pounds, C is the specific heat capacity in BTU per foot degree Fahrenheit, and delta T is the change in temperature in degrees Fahrenheit. How many kilocalories of heat must be added to 10 kilograms of steel to raise its temperature 150 degrees Celsius? The data for the problem. We need the specific heat of steel, which can be found in Appendix C of your book. The specific heat capacity of steel is 0.115 kilocalories per kilogram degree Celsius. The mass is 10 kilograms, and our change in temperature is 150 degrees Celsius. The working equation is our specific heat formula. Our solution is 173 kilocalories. How many joules of heat must be absorbed to cool 5 kilograms of water from 75 degrees Celsius to 10 degrees Celsius? Our data for the problem is the specific heat of water, which is 4,190 joules per kilogram degree Celsius. The mass is 5 kilograms, and our change in temperature is 65 degrees Celsius. The working equation is the specific heat formula. The amount of heat absorbed is 1.36 times 10 to the 6 joules. Specific heat affects weather. For Europeans, in addition to warm jet streams in the atmosphere, current in the Atlantic Ocean carries warm water northeast from the Caribbean regions and retains much of its internal energy long enough to reach the North Atlantic Ocean. Energy released is carried by westerly winds over the European continent, keeping it warm in the winter and cool in the summer. London is farther north than Nashua, but has milder winters and cooler summers. When two substances at different temperature are mixed together, heat flows from the warmer body to the cooler body until they reach the same temperature. This is known as thermal equilibrium, or the method of mixtures. By formula, the amount of heat lost by the warm object must equal the amount of heat gained by the cold object. In the equation, L refers to the warmer body that loses heat, and G refers to the cold body that gains heat. T sub F is the final equilibrium temperature of the mixture. A 10-pound piece of hot copper is dropped into 30 pounds of water at 50 degrees Fahrenheit. If the final temperature of the mixture is 65 degrees Fahrenheit, what was the initial temperature of the copper? We write down what we know. We know both masses and the specific heat of copper, which is 0.093 BTU per pound degree Fahrenheit, and the specific heat of water at 1 BTU per pound degree Fahrenheit. We also know the initial temperature of the water, 50 degrees Fahrenheit, and the final temperature of the mixture at 65 degrees Fahrenheit. We do not know the initial temperature of the hot copper. The basic equation is the specific heat equation for mixtures. The working equation solves for the initial temperature of the copper. This takes some algebra. Substituting what we know into the working equation, we find an initial temperature of the copper at 550 degrees Fahrenheit.